Okay, so thank you so much, everybody, for coming today to see our speaker. This is Dr. Steve Heim. Steve Heim is a research scientist with the Biomimetic Robotics Lab at MIT. Parenthetical United States, Steve wrote, because he's on world tour at the moment. His next speaking engagement is in Sydney, Australia, down under. So we're very lucky to have caught him on this hemisphere for now. He's interested in understanding dynamics in biology, especially how and why animals learn to move the way they do, and to leverage these insights to design better robots and algorithms. Previously, Steve was at the Max Planck Institute for Intelligent Systems, that's in Germany, in case you're following along on the map, and where he completed a postdoc with the Intelligent Control Systems Group and his PhD with the Dynamic Locomotion Group. He obtained his master's degree and bachelor's both from ETH Zurich, Switzerland, with stays at Tohoku University, Japan, EPFL, Switzerland, and TU Delft, Netherlands. He is a citizen of the world, and we're very lucky to have him today. Please welcome Dr. Steve Heim.
Thank you for organizing this and for the very colorful introduction. And thank you everybody for coming here. Okay, I'm talking a lot about learning and hierarchies, but as Sabrina already pointed out, my big picture motivation is is to understand how animals, why animals move the way they do, and the approach is through robotics is, can we build it? Can we understand it better by actually trying to reproduce the same kind of agility and motion and elegance that we see in nature? Now, one thing I do want to point out, the rest of the talk is going to be rather conceptual and a little heavier on the algorithms and math side. The part that I'm not showing, but is actually taking up maybe 80% of the time, is it really starts with a lot of experimentation and actually get your hands dirty and do things on hardware. You'll see in the bottom left corner, this includes a lot of just failures. And all of these failures are really important steps to actually getting to that understanding. So I just want to point that out. And there's also a lot of work from a lot of different people I've been very lucky to work with. So to start with, actually,
You click OK, hopefully it'll leave you alone.
Oh, there we go. Perfect. So addressing a bit this gap between what we see in biology and our modern robots, this is one of my favorite videos. It actually plays. Okay, there we go. So this is a predator-prey interaction. So it's really a moment of top performance, right? And there's this moment here where this elephant shrew slips and slides, pretty much loses all control authority, and just keeps on going. And that's really remarkable, right? Now, when I first started my PhD many years ago, I used to use this video to motivate why we need more robustness. But if we look at the current state of the art, so this is from about a month and a half ago by Unitree Robotics. It's a very different system. It has actuated wheels. It can compensate for the loss of traction, things like this. But in terms of robustness, it's actually really, really good. So are we actually already there? Have we already closed this gap? And where I still see a gap, and I think I've been seeing this gap actually get bigger, is how we actually achieve this performance. So a lot of the breakthroughs in modern robot control have really been driven by machine learning and modern machine learning algorithms that are really built on the assumption of really large data sets, a lot of compute, pretty much always done all in simulation and then deployed zero shot. And this really, this is really different from how animals have to learn. So this elephant shrew, for starters, can't just live its life in a dream state, then suddenly wake up and start performing. It has to be somewhat functional pretty much from the get-go. Then it has to learn pretty quickly from single stream data. That means the amount of samples it has is very limited, and especially that distribution of samples is really limited. And improving that distribution is actually really expensive. It has to always deliberately decide, am I going to try something new, at the risk of injury, at the risk of not surviving? And so it has to be really sample efficient and make sure those samples are really meaningful. If we look at compare the architectures, biological neural architectures tend to be a lot more robust and resilient. I can tell you how much time we spend just tuning hyperparameters, designing really custom reward functions. That really takes up a significant amount of time. You update the physics engine and you have to do it all over again, right? It's really a little bit brittle. And finally, the role of embodiment tends to be a lot more prominent in nature. So evolution has really iterated on not just the hardware, but also the software and the learning mechanisms all together, which is also very different from modern machine learning, which is kind of one algorithm fits all, right? So these are kind of the key themes that I want to explore. And so the driving question is like, can we actually get this learning, just like in nature, and largely through bioinspiration, do this learning directly in hardware from single stream data? There are a lot of pieces that are going to have to come together for this. I'm going to talk to you about three things I've been focusing on today. The first is the importance of hierarchy and a hierarchical structure in our learning. This is my current and it's going to be my immediate future focus. The second is the connection between morphology, between the hardware design and learning. So this is going back to my doctoral work on understanding how morphology or your system design influences how easy it is to learn. And finally, I'm going to show you how the math that I developed for this question can actually be used as an estimate of how confident we can be. We're going to take this full circle back into the hierarchy to do this kind of active learning and really go get samples only when and where we need them. Okay, so for this first part, I'm going to show you a couple of very recent projects from a couple of students I've been supervising at MIT, where I've been effectively running a sub-team as a research scientist the past few years. So this first project is work with Jenny Zhang, who is a fantastic master's student who's now working at an autonomous driving startup. And the core of this project is to use oscillators as an internal model, so effectively an internal representation that lets us describe to the algorithm we want you to move with a good gait without us having to specify exactly what that good gait should look like. So what do all of these words mean? So when I say gaits, what I'm thinking about are these gait diagrams, usually attributed to Hildebrand, although you'll find them in literature over 100 years earlier. The way you read these is each row represents one of the feet. So here we have the left hind, left front, and right hind foot. And then the black bars indicate when that foot is on the ground. So when it's in stand space and supporting the body weight, and when it's in swing. Yeah?
Can I ask questions?
Yeah, please.
So I know in human gait is actually somewhat unique to individuals, meaning it's not like one algorithm fits all.
Yeah.
Everyone has partially because of physics and partially because of other things. And here you're trying to put everything into one particular type of algorithm.
So I would make a distinction in any case between the algorithm and the output, right? So the gate is the output.
Yeah.
So the same algorithm, we can have different gates emerging from, which is what I'll kind of show.
Okay.
You could also have different algorithms converting to the same gate or giving you different things, right?
Sure.
Yeah.
Okay, so you're going to get different gates out of this.
Yeah, so this so far has nothing to do with the algorithm. This is just how we analyze how is the robot or the horse or whatever the system is, how it's moving. Yeah, does that make sense?
Yeah.
It's more of an analysis tool.
Okay.
And the way we're going to use this analysis tool is, so kind of to your point, what's important here to define gates is not the specifics of these black bars. It's really the pattern or the sequence, right? So if the black bars are a bit shifted, they're a bit different, there's some variance between individuals, as long as the pattern of the sequence of these black bars is the same, we're still going to say it's a trot or a pace, etc. Does that make sense?
Mm-hmm.
Okay. So we're going to use here, we're going to make a little vector space. We're going to take one of these feet as reference, so in this case, the right front foot. We're going to take the timing difference between the footfall of each of the other feet and the right front as our coordinates. This gives us a little 3D vector space, and now we can have a little Euclidean distance to do a very simple classification of which gate we're currently using. Okay, so you can cache this in the back of your head for now. We're going to bring it back in a few slides when we actually do the analysis. But the key thing I want you to take from this is these diagrams. This is what I want those oscillators to represent. This is what I'm after. This is what I want to be able to describe to the learning algorithm. So what are these oscillators? I'm going to explain this with central pattern generators, since this is a much more common paradigm. So central pattern generators, or CPGs, are actual neural networks often studied in a lot of organisms, typically responsible for rhythmic movements or rhythmic excitations. In robotics, we're pretty much always going to abstract these out as a network of oscillators. Right? So in this case, we have 4 oscillators, one for each leg. and they're coupled. So they have, each oscillator has a state, a phase that lives between 0 and 2 pi, goes round and round. And then we have some dynamics. So we have a base frequency, which is the same for all the oscillators. And then we have these coupling functions, so these blue arrows. And as engineers, we can go in and design those coupling functions so that the oscillators will actually synchronize to a specific pattern. So for example, one of the gate patterns that we just saw before. And finally, we can map the gates, the phase from these oscillators to something that's relevant to the robot controller. So basically, it is prescribing, a typical example would be to prescribe what is the actual movement of the foot that we want. Okay? So we're not going to use these central pattern generators. We're going to use decentralized oscillators. So what that means is our first step is we're going to cut all of those connections. And instead, we're going to replace them with some local feedback. So we're going to measure the ground reaction force, essentially the load that each leg is feeling, modulated by each oscillator's own phase, so this part here. And what's remarkable with this is, even though we've cut all those connections, these will still synchronize, right, to a specific gate.
The connections are still there, you just have an indirect variable.
How?
The ground.
Exactly, right?
Yeah.
So they're still indirectly coupled through the physical interactions. And what essentially happens is the dynamics of these oscillators will entrain to the actual physics of the system. And the way to interpret, kind of intuitively interpret this modulation term is you want to interpret the top of the oscillator as it should be in swing, the bottom as you should be in stance. So if you have ground reaction forces in this half, well, clearly this leg is being used for stance already, so we should accelerate the phase towards the bottom. If you have ground reaction forces in the other half, clearly it's still being used to support the body weight, so we should slow it down and try and keep it in that bottom. Now, I've told you that they synchronize, and they do synchronize to a gate, but this is the reason I really love this model is this is a really simple feedback term, but I would dare anybody to predict from this which gate it actually synchronizes to. And that's what's beautiful about this is that it actually really depends on the coupling, the entrainment to the actual physical dynamics. It really depends on the morphology, on the terrain, and all these things. So to give you a bit of context, this was pioneered by Akira Shiguro's lab. I actually spent some time there when I was at Tokyo University in Japan, and actually helped take these videos back then. And as you see that you don't actually just get emergence of different gates. In this case, they get a walking gate. You actually get spontaneous transitions between gates. So here, the only change is they increase the base frequency, and it naturally switches from a walking gate to a trotting gate without actually an algorithm or some sense of optimality of what you should do. Now, one thing that's always bothered me of these is that it's using an internal model, a simple model, in a very prescriptive way. And this is really going back to this philosophy of should models be prescriptive or descriptive, right? And I do feel like a model, you're using it to make predictions, so this should be descriptive. Those predictions can always be wrong. Right? But this mapping here is really telling the robot, oh, you have to behave exactly like what the oscillators are saying. So we want to get rid of this part. The way we do this is start with a very standard deep reinforcement learning pipeline. We're going to augment the environment with these oscillators. We're going to provide observations of those oscillators to the policy. So this lets the policy, which is a deep neural network, use those observations, but it's not telling it how, right? It's still up to the learning algorithm to figure out how to use those observations. And finally, we're going to add some regularization where we add basically a shaping reward that says, well, if you have ground reaction forces in this top half, then you get a small penalty. And if you have ground reaction forces in the bottom half, you get a small reward. Yeah?
How does this work given that it's supposed to be a Markov decision process and here you have the feedback?
I didn't catch the first part. Given that you...
So the environment itself is supposed to be a Markov decision process, yes?
Yeah.
But here it seems the feedback has to rely on the history of what happened with the oscillator touching the ground, because there's no connection, right? Is it the case that there's a notion of history here?
So there's no history. I'm pretty sure this is still Markov. You're saying that the oscillator state is not Markov.
I thought that it wasn't because I thought it depended on what was happening before in terms of I was touching the ground. I'm no longer touching the ground.
Right. I'd have to think more carefully to really see if there's a case where it's not Markov, but I'm pretty sure it's. Let me give you two answers. In practice, Markov very often doesn't matter. And it's been frustrating. Like there are things that we don't give it the full observation and it actually does better, which has been very frustrating. But in this case, I'm pretty sure that the oscillators are fully Markov because you don't observe this part, right? But you observe the actual dynamics. And you do observe all the physical states that you would need to actually infer this, right? We're not observing the actual ground reaction force, but we do observe the kinematics and all these things. So I would be pretty confident saying it's still Markov.
All right.
But we can talk about that more offline. But yeah, so we have this shaping reward, but at the same time, we also still have all the standard task rewards. So like track your forward velocity commands, stay upright, don't fall over, these things. So essentially what this shaping reward is doing is basically do what you need to do. And if you can do it while still doing what the oscillators are also expecting you to do, then you can get a bit of a bonus.
Now you compose these two components of rewards?
They're just some. It's just an additional reward. So typically, if you do this kind of learning, you also need a bunch of shaping rewards. Like don't drag your feet. Have at least this much swing time. We can get rid of most of all of those rewards, and it's not really that we're getting rid of them, but this is kind of the idea of why this representation is really important. This is the oscillators just give you a representation that's very convenient to express all of these rewards in one simple function. It's kind of the key.
How do you determine the rewards?
Trial and error.
Okay, so you look at it and say, this looks good.
Yeah, so for this one, this is very much inspired by, okay, this is what we want those oscillators to represent. So let's write a reward that says, hey, if you're in swing when the oscillator thinks you should be in swing, that should be a reward, right? And then the sinusoid is there to kind of just smoothen things out. And that's, we did do it as a step function at first, and it still works. It's just not as, doesn't learn as well. So having the sinusoid kind of smoothens it out also so that if you touch down around here, that's rewards almost zero anyway. So it makes it a lot more kind of flexible in that sense. You could design it a little bit differently as well. At that point, it's kind of just trial and error.
I would think the rewards would significantly alter the behavior.
So generally, yes.
Yeah.
The rewards on this tend to be very robust.
Okay.
So I think the ones in the code that we published are relatively weighted very relatively high, but actually we changed them up and down like an order of magnitude and behaves more or less the same. Qualitatively,
Right.
behaves the same. Yeah. So what we get with that is, typically we'll start it in a trot, and we get these very nice, very natural looking changes in the gates, which is very satisfying. So yeah, in the paper then we do a full ablation. We look at, okay, if we cut each of these signals, what's going to happen? I won't go into all of them, but the one I want to talk about a little bit more here is what if we cut the coupling? So that coupling from the actual dynamics up towards the oscillators, right? So I'm going to annotate these like this with ORC signal 1. What the way to read this is ORC 110 means that we are training with the observation and reward, so with these two signals turned on, but this one turned off during training. And then the sigma equals 1 is we've turned the coupling back on during evaluation. So let's start with the standard setting where we have everything turned on during training and during evaluation. So as we kind of talked about, this is our gate diagram. Each dot is representing a robot that's initialized with the oscillators in some random configuration. And we see that they do all converge towards this cloud around tribe. We can do a first sanity check where we train with everything turned on, but we cut the coupling at evaluation. This is essentially checking that the policies actually care about what the oscillators are doing. It could be that the policy just always tries to trot and ignores the oscillator observations. Come on in. And we see that it doesn't, right? If the oscillators aren't converging, aren't constraining to anything, the policy does actually try to move the way the oscillators are asking. Finally, the case that I pointed out, this is trained without the coupling, but we turn on the coupling afterwards. So as we should expect, turning on the coupling does have the oscillators entrained to the physical dynamics. But differently than when we train with the coupling turned on, the entrainment is a lot slower. And we still get these clouds that are basically local minimas, like these shallow local minimas in the phase space of the oscillators, where it doesn't quite escape, it doesn't converge as cleanly and as neatly to the gates. So the way we're interpreting this is that this really suggests the importance of not just having descending pathways, not just having a hierarchy where the signal goes down, like the high level is commanding everything towards the low level. This coupling upwards is actually, it's a weak coupling, but it's an actually really important coupling. And the policy learns to manipulate through the physical dynamics to actually also control the slower dynamics of the oscillators. Right? It can actually guide and shape the potential landscape of the oscillators to make these cleaner, nice values, essentially, like bases. Okay, so where are the hierarchies in all of this? Well, in the beginning, the hierarchy is just Jenny with a remote control telling the low-level policy go forward, turn right, stop, do all these things. One thing that's nice is that the robot actually does stop without us having to have a lot of reward shaping. This is notoriously difficult in legged robots. And what happens is that the oscillators will actually converge to the bottom and just stay there. It finds an equilibrium point. What's annoying is that when we start it up again, because the oscillators are all synchronized, it starts in this really janky kind of pronking gait. Now, it will converge back to a trotting or a half bound if you give it enough time, but it takes quite a few gate cycles to get there. It's kind of annoying. And this is where we realized, instead of going back to reward shaping and telling it, oh, well, if you're starting from 0, you should actually ignore the oscillators for a bit or something like this. This made us realize we want those oscillators not just as an internal representation, we want to use it as the interface between the high level and the low level. And this pretty simple change in architecture starts to give us a lot of the properties that we also see in biological neural architectures. So I think my favorite is something called partial autonomy, where you can basically turn off the high level and the low level will still just keep on running. Right? So in this case, basically the oscillator has different steady state behaviors. So for example, that equilibrium point where it's standing still, and the high level can be turned off for that. Then when you want to start it up again, the high level can say, well, I'm going to increase the base frequency, and then I'm going to push one specific oscillator, right? So for example, the front right oscillator, push that forward. And it's up to the low level to figure out what exactly to do with that leg. But it knows, oh, the high level wants me to start moving forward and start with this leg first. Okay. And once it gets into the steady state of actually running forward, the high level can turn off. This is kind of like if I go for a run, and I get to some steps, I'm going to be consciously thinking about where am I putting each foot. But most of the time I'm running on flat ground, I don't have to think about running, right? And start just daydreaming about what I'm going to have for dinner or that talk I'm going to have to give soon, right? And it frees up the high level reasoning to think about other tasks. Okay, so as we were wrapping up this project, I started working with another really good master student, Chen Hao, who's now doing his PhD at ETH Zurich. And with this project, we basically said, can we take all of those lessons learned from these oscillators and go full machine learning with this and actually learn those oscillators instead of designing them by hand. So the paradigm we're using here are autoencoders. So the way this works is we have our inputs. In our case, these are trajectories. We're going to pass this through a first neural network encoder that compresses this to a lower dimensional representation. And then a typical autoencoder will then decode this and use the difference between the input and the reconstruction as our training signal, as our loss. Use this to backprop through both neural networks. the key insight that we're basing this work off is from this really nice paper from the graphics community, where they realized, well, we're representing a lot of very cyclical motions. Let's add some strong inductive bias, add some structure into that latent representation using a fast Fourier transform. So basically we're parametrizing the latent space trajectories with sinusoids. So when we saw this, we said, aha, well, that looks really familiar, right? We can take the time derivative of those sinusoids, and this gives us oscillators. When we first just implemented this, it didn't quite work that well. And what we realized is, unlike for the graphics where we're really just they were trying to add spatial structure, we want to use this as a predictive model. Right? So that means we want those predictions that come out of this model to be accurate. Luckily, that was really easy to fix. We basically add a predictive loss. So we are going to take those oscillators, roll them forward, and then decode those predictions, and then also add as a loss the error in the prediction and what actually happens. Okay. Then once we've trained this, so this is trained offline with a data set that we had already gathered, we can then plug this into our standard deep reinforcement learning pipeline, learn a low-level controller, and then, just like we talked about before, learn a high-level policy that interacts with the low-level policy through this latent dynamics model. And basically manipulating the parameters of these sinusoids to essentially manipulate the manifold that the latent dynamics are living on. And this works pretty well. So what you see here are, in the inset, are what the oscillator predicts should happen, what they think is going to happen. And then the main video is a physics simulation of the low-level controller trying to track this and actually trying to do this. And we get these pretty nice, you can interpolate through that space pretty nicely. So it makes the learning with the high-level policy a lot simpler because of that. Okay, so key takeaways here are really two. The first thing is the importance of not just learning a latent representation, but actually using that dynamics model. We're trying to do dynamics, so we should really leverage that. And the other thing is choosing the right time scale. So we did a lot of work with oscillators, with initially thinking about, oh, we want to put in that quasi-periodicity as structure. What we've realized in the meantime is that quasi-periodicity is not actually that important. We've tried this with things that are not cyclic, and it actually still works really well. And what we've realized is these oscillators expose the timescale as one of the main tuning parameters by exposing the base frequency, right? And getting that timescale right is what actually is really important. And this parameterization just happens to be really convenient for learning that timescale. And this change in perspective has been really, really important in how we approach reduced order modeling. Okay, with that, I think I have to rush a little bit. You have 1 hour?
Yeah.
We usually start this.
Oh, I didn't restart the clock. Okay.
You're-
Okay, so let me switch gears into morphology and learning. So the math behind all of this is something called viability theory. I'll explain what that is in a moment. But really the key takeaway I want you to take is I think we should be more deliberate and more conscious of when we use metrics compared to when we use measures. So with that, can I get a show of hands who already knows what's the difference mathematically between a metric and a measure? You've seen this before, you don't?
I don't remember. Go for it.
Really?
No.
I'll give it a shot, right? I'll give it a shot. So the metric is essentially the ground truth metric of what you ideally want to control or measure, while the measure is really the compressed representation in terms of a mean, an average, or a median. Is that
Not what I'm going for. So we're talking
from mathematical definition.
exactly.
Yeah.
So the good thing is, first of all, this is pretty much the response I get every time I give this presentation. But also, all of you are, I'm pretty sure all of you are actually familiar with this. But to my point, we should be more conscious about what's the difference and when to use which one. So a quick refresher, a metric is simply the notion of the distance between 2 points and has certain properties. In terms of control, this is basically the error. We know where we are, we know where we want to be. That error is a metric, is the distance to where we want to get to. And the purpose of control is to drive that metric to zero, drive the error to zero. This starts to have problems when we are starting to compare trajectories, right? So for example, if we have this limit cycle, we want to know which point is closer to that limit cycle, and we just look at the metric, the Euclidean distance, for example, between that point and the closest point on that limit cycle, they might seem equidistant. But if we look at the orbit of this system, which I completely made up, but we'll see that, oh, one point, they're both on the same orbit, but one point is earlier in time. So somehow we would want to say that the point that's earlier in time is farther away, but a Euclidean distance in state space doesn't really tell you anything about the dynamics.
Change of space.
It's really hard to do in a way that's actually useful, at least in my experience. A measure, on the other hand, is the notion of the volume of a set. So, for example, in controls, you have a region of attraction. This is the set of all the initial conditions that will converge. So the measure is the size of that region of attraction. So now you might compare your controllers in terms of a metric, how quickly they converge, or a measure, how big is that region of attraction. Okay, now let's go to viability theory. Viability theory starts from the opposite view. Instead of thinking of where we want to be, we're going to start by thinking of where we never want to go. We're going to define a failure set, a constraint in state space. Okay. And just from this definition and the actual system dynamics, naturally emerges the notion of a viability kernel. So there's a set of all the initial conditions where you can stay inside that set, and therefore you can avoid failure forever. So another way, it's the maximal positive invariant set. So if you're inside, you can have policies that move you around inside the viability kernel. You can also leave, but once you're outside, you can never get back in. So that means once you're outside the viability kernel, within finite time, you have to visit failure.
This is not unique, this kernel, is it?
Yes, this is the biggest possible.
Were you saying maximal rather than maximum? So it seems like it's.
That was my sloppiness.
Oh, okay.
Yeah.
Sorry.
No, you're good. Yeah, maximum. It's the biggest positive invariant set.
Okay.
Yeah, so this is all from just the system design. We haven't talked about the controller yet, right? So when we design a controller, what we're trying to do is generate a region of attraction that converges to a given behavior. But by definition, this has to be a subset of the viability kernel. So now you might think, okay, that measure might be the volume of the viability kernel. We want to design a system where this is as big as possible. What I'm going to argue and try to convince you is that actually we want to add some structure that makes it easier to find controllers. And to find that structure, we have to go into state action space. So let me explain that with this really simple toy model. Imagine you have this little hover ship that lives in a one-dimensional world with just 5 states, 1, 2, 3, 4, 5. State 5 here is our failure set, so crashing into the ground. This is really lagging. Are there a lot of people online, or can I just wave at the?
I don't know.
Okay, well.
But it's recording, right?
Yeah.
Yeah. Okay, I'll try to use the mouse. So, these are our natural dynamics. These arrows are just some weird gravitational pull, and these are our actions. So we can do nothing, apply a thruster, or apply double thrusters. The way you read this is, and these are. Okay. These are our dynamics. So the way you read this is if you're in state 1 and you do nothing, you will end up in state 2. So you will move down in state space. Okay. So for this system, it's simple enough. We can find the viability kernel just by inspection. These are states 1, 2, and 3. State 4 is not viable because no matter what we do, we will end up failing eventually. Okay. So far, this is standard viability theory. The first key step I took is to extend this into state action space and find the set of state action pairs that map back into the viability kernel. So these are both sets, and they share a very simple but really important relationship. The viability kernel is always the projection of the viable set into state space. And this gives it a recursive property where you can kind of think of the viable set as a very coarse predictive model. So if you pick something from the viable set, you don't know exactly where you'll end up, but you'll always end up in its own projection, and therefore you can always pick another action from that set. Okay. Now what's the advantage of having a set? Well, if you have a set, you can put a measure over it. So the measure we're going to use, let's try to get rid of this again. No. Yeah, oh well, we'll live with it, I guess. No. Well, the measure we're going to use is we're going to pin each state. We're going to look at the slice of actions available from that state, and we're going to put a measure over that slice. So what that means is up here where this measure is very large, and we don't know what the best action is. We haven't defined what optimality means yet, but we can explore very aggressively. We can try anything we want. Everything is pretty much safe. On the other hand, down here where this measure is very low, it means that if we get there, we have to be really careful. And even if this happens to be the optimal state to be in, it's actually really hard to learn the controller there, because any kind of exploration, anything I try, has a very high chance of taking me outside the viability kernel and causing me to fail. Now we can take this one more step and map this measure back into the state action space. This is giving us essentially a one-step forward prediction of what that measure will be in the future. And again, we have this, this simple recursive relationship where if I only take state action pairs that have at least a certain amount of measure, we'll end up in the projection of that superlevel set. So this means we can apply this in a feedback manner without having to actually roll out trajectories like an MPC and actually enforce that constraint along the trajectory. Okay, let's step through this again with a slightly more interesting model. This is a spring-loaded inverted pendulum or slip model. This is very commonly used in biomechanics to understand running, also used very often to design running controllers for robots. If you're familiar with this model, the state we're using is the apex height once per step, and the action is the landing angle of attack of the leg. If you're not familiar with this model, don't worry about it, it's not that important. But we've basically done some pretty standard modeling tricks to reduce this to one state and one action. So just like before, we have our state on the vertical and our actions on the horizontal. Okay? So this is our dynamics map. So the way you read this is for a given state, if you pick in a state action pair that's in this blue, this cool colored region, you'll end up going down in the state space. If you pick something in this warm colored region, you will go up in the state space. Everything on this intersection, these are our limit cycles, you'll end up at the same state. And if you pick anything that's in this gray region, it means you're going to fail. You're going to face plant. Right? So this on the side, this is our viability kernel, a set of states where we can avoid failure forever. Just like before, we're going to take as our viable set. This happens to be the threshold of that entire colored region. And then we're going to pin for every state, take that slice of actions. This is going to be our measure. We're going to colorize this to make it interpretable and map that back into state action space. So at this point, I hope it becomes clear why we need to care about measures and not just metrics. Right? So a typical thing to do if you're doing robust control or safe learning or things like this is you assume you have some safe set, which is already a pretty strong assumption. And then you say, well, if I need a little more robustness, let's add a margin. Let's stay away from the edge by some metric. And what we see here is that not all edges are equal. Okay? So there are some edges, like up here, where you can stay pretty far from the edge, and it's still really difficult to actually avoid failure. And there are other edges where you can get really right up to the edge, and even despite that, it's still really easy to avoid failure. It's still really easy to stay in this region. So depending what you're actually looking at, you really should, sometimes you want to consider a metric, sometimes you really want to be able to. This is done before we've actually done any of the controller design. So now we can compare different systems. So for example, this is essentially the same system, but with a nonlinear spring that, as you compress it, tapers off. And the color map here is renormalized to be able to compare them. And we see that not only you have a lot more space to design your controller, but all those controllers tend to be a lot more robust. It's just a lot easier. So with this nonlinear spring, you can actually explore much more aggressively. Okay, I'm going to gloss over the next project, but we essentially use this to actually do a biomechanics study. This is based on a pretty famous experiment from this group at Harvard that looked at running guinea fowl and how they stabilize against step up and step down perturbations, modeling this with a spring-loaded inverted pendulum. I worked with Matt Millard, who is a biomechanist, looking at muscle modeling. And there's been an open question in muscle modeling of, we know it behaves like a spring, and that's really important. We know there's also some damping. It seems like this damping is tunable, but it's very small. It's very unclear if this is actually functional or if it's just can't avoid damping in a physical system. So Matt came up with this very elegant, very simple model. I'll skip over the details, but essentially we, in simulation, reproduce this step up and step down study. And after the perturbation, we use this measure to look at, okay, if it had this perturbation with a given damping, how easy would it be to recover after that at the next step? So we start with the nominal, we pre-compute the viability measure. This is on a Poincare map. We're going to apply those step up and step down perturbations, look at where at the end of the trajectory, so map basically the last time step up the trajectory onto the Poincare map. We're going to repeat this for different values of damping of the system, and then we can compare these. So each line here is the model with a different value of damping. And the color and the height is basically the viability measure after the perturbation. And what we see is that adding a little bit of that damping actually really increases both the amount of perturbation you can recover from, but also how easy, especially how easy it is to actually recover. That volume of actions is much easier to pick from. Right? But we also see that this effect plateaus pretty quickly. So that really small amount of damping that we see in biology, this actually matches the actual dynamics of what's functional. So you only need a little bit of damping and you get pretty much all of the benefit. And for what it's worth in robotics, if you're having something that's really hard to control, typically adding a bit of damping to the system really helps stabilize things. You kind of get the same effect. So yeah, that was with human parameters. We actually matched this then to actual guinea fowl data from the originals paper and reproduced it. One caveat with all of this that you may have noticed, I've been showing you very simple models. We have been able to scale it up a little bit, right, 4 or 5 dimensions, but the algorithm we're using is basically like value iteration, so this really runs into recursive dimensionality pretty quickly. But in my first postdoc, I got to work with another really good master's student who actually stayed in that lab for his PhD and should be graduating this year. So fingers crossed. But he had a background in applied mathematics, and together we looked at making connections between viability theory and value functions. And I won't go into any of the details of this body of work, but the exciting thing is if we can get this from value functions, then we should be able to hit this with deep reinforcement, right? So this is what I'm going to talk about next. We're going to drop a lot of the rigor of actual viability theory, but we're going to keep all these ideas of what we care about is this measure of how easy it is to actually do what we want to do. Right? So this is going back into this hierarchical framework. So just as a reminder, what we have here is we have an internal dynamics model that we've pre-trained. We have a low-level policy that we learned to track the internal model. And then we have a high-level policy that is basically controlling that internal dynamics model. So what we're going to do here is, in parallel to training the low-level policy, we're also going, we're going to also learn a confidence region. And then we can use this estimate of how confident we are to basically design a fallback trigger and decide when to actually follow the high-level commands and when not, when to ignore it. Right? So what this looks like is, okay, so if the high level is turned off, right, if the high level is not doing anything, the internal dynamics model is just going to step forward. The high level can push this around in that reduced order model space, state space. If it decides to push it out, and we can use that one step look ahead to detect that it would actually go out of the confidence region, then we can basically ignore it and just step forward with our dynamics model. So we don't need to also have a backup controller. We just follow that internal model. And this is essentially giving us a confidence estimator that lets us push to the edge of what we can actually execute safely and confidently without going completely out of distribution. And so this gives us a way to basically execute the closest thing that is meaningful. So this gives us safety when we're actually executing it, but especially gives us trajectories that are actually still useful. So, or like still pretty high quality. So on the right for you is without the fallback. What you see is this is what the high level is commanding. So in the center there, data set. And this is often trying to give it, this is sometimes giving it something that it knows how to track, and often giving it something that is out of distribution for the low level. And what happens here is that if it's out of distribution, the low level policy still manages to be robust and avoid falling down, but it doesn't know what to do, and it starts to basically go back to motor battling. Instead, here we can actually still do the simplest or the most similar thing that we can actually execute well. This is exactly what we want to actually enable this more sample efficient active learning. And okay, that's how are we?
Pretty much
I think
out of it.
I think I'll stop there and happy to take any questions.
Thank our speaker.
Questions?
Perhaps a quick thing, right, on these oscillators, because they are a bit of a new beast to me at least. Are these relatively cheap device to integrate in robots? So they come in all sizes, or they are constrained to sort of larger, more expensive robots? Number one. And second, when you showed the first picture of I think it was a chipmunk running around, right? Not only you care about kind of longitudinal forces, but also lateral ones, right? Are those oscillators able to capture those, or they are sort of unidirectional?
Okay, so let me start with the first one. So the dynamics of the oscillator is really abstract, right? So the dynamics is basically just integrating this. So that's super simple. You can do that on an Arduino if you want, or whatever you want, right? So that's actually you can use that on pretty much any system, as long as you have some sort of ability to do numerical integration.
Right, but you are measuring something there, right? You're measuring a force.
Yeah, so for this feedback, excuse me, that's where it gets a little bit trickier, and it depends a lot on your system. So for CPGs where you're not having this feedback, then it's pretty simple. But here it depends on your sensor, right? What we're doing with the mini cheetah is we don't actually have a dedicated sensor. We're estimating the ground reaction force through the inverse kinematics and the joint torques. This works for us because we have a system that has very low gear ratio. So the motor current is pretty much directly proportional to the actual.
So you're measuring, I see, you're measuring the current. So you're measuring the power you give to the actuators to be able to be in a certain position.
Right.
I see.
So if you have a high gear ratio, that's not going to work because you have too many velocities. Yeah. But with a low gear ratio, this maps pretty well. So it's a little bit different from the measurements we get in simulation. And that has been, everything works. It's just qualitatively a little bit different, sim to real. But generally it's been pretty robust.
Isn't that in this case subject to things like actuators where you're now friction building up or debris getting caught in the gears, and then you need more power. So that can throw off your calculation after.
Yeah.
But I got you. Yeah. Understand how you do it.
But that's actually one of the reasons I like this so much is these oscillators are giving you this level of abstraction that becomes a lot more robust to those changes, right? And it's also always kind of just entrained to the actual physics. So if you get that kind of wear, even if you didn't have these oscillators, the robot behavior is going to change because all your other controllers are also depending on this, right? And here you have a system where the slower dynamics of the oscillator is actually kind of entrained to that change as it's happening. Yeah. I think you had a second question that I didn't answer, but.
Yeah, about lateral forces versus longitudinal forces, but I think it's kind of captured already in your answer. You just have to isolate it.
Yeah.
So I saw 2 and 4, like you tried 3, 5.
I can show you a video later. Yes. So,
Okay.
well, yes and no. We haven't tried it systematically, and we haven't really looked into it super a lot. We have done a little bit of just, what if we take off one leg, one leg is broken.
Right.
And it works pretty fine. It does, sometimes you have to retune things a little bit, or you have to relearn things a little bit, but generally it's pretty robust to that. One thing that was almost annoying is that when you cut some of those signals, in particular, if you remove the reward, it'll often actually run with just like 2 legs, which in simulation looks like, oh, that's for sure just exploiting some simulator physics, right? It's no way that's going to work. And we put it on the robot, and the robot did exactly that. And it looks horrible. It's just like dragging a leg. And just... but the sim to real has been shockingly good. But yeah, more to your question, Akio's lab, they were using this kind of model also on up to like centipedes or snake locomotion, usually with some changes. So once you get to a lot of legs, you'll usually add some local coupling between the oscillators. So you, compared to CPG, you're not networking the entire oscillator network, but you'll have some neighboring feedback. Yeah, so it's not usually connecting the oscillators directly, but you'll have the ground reaction force from neighboring legs also feeding into your oscillator. And that that's really effective to get these like traveling waves that you often see in centipedes or snakes or anguilliforms or things like this.
You could also do this for wings.
Yes, I haven't seen that in robotics. Yeah, yeah. I know that that has been studied in, say, like not fireflies, dragonflies and fruit flies. I haven't checked. I'm not sure that it's been used in flying robots. I haven't seen that. But yes, it's essentially anything that's
or drones where you're looking at you're measuring. I mean, you can just like you're measuring the actuator.
Yeah.
You could do the same thing with the different rotors and the drones.
So I think what's key there is you have a certain frequency that you're, or like a certain time scale that you're trying to target with these oscillators. With the quad rotors, you're usually kind of at a constant thrust. So I'm not sure that this representation is really helping you find that time scale.
Yeah.
For anything that's flapping, I think
Yeah.
it's a much more natural representation.
Yeah.
Oh, sorry, yeah.
Sorry, so the measure you have for viability, it's counting how many states I can go to that are within this viable set. Is that what it's measuring?
Essentially, yeah. So for the example I showed with the street, so we're just counting. Otherwise, you would use a Lebesgue measure and actually, yeah, take the measure where it's at. But essentially, yes.
Okay, and you made the connection between that and value iteration, right? It kind of looks like a value function, but it's not a discounted sum.
It's not technically a value function. So implementation-wise, the algorithm looks very much like value iteration. So that's why it has the same challenges as value iteration, as in you're iterating over everything. You're basically doing brute force. That's the connection there. But the connection to value functions, we actually have a paper called Safe Value Functions that is explicitly making these connections. You can come up with a specific formulation of the optimal control problem that makes this equivalent and also makes things like control barrier functions and constraint MDPs equivalent. But it's not always, and it's not technically a value function in the standard sense, in the standard optimal control sense. Happy to talk about that more in detail offline. I think it'll be easier offline.
Thank you.
All right, let's thank our speaker one more time.